Let's start the lecture. Agenda for the lecture is to recap essential ingredients of Newton's law of gravitation, which we are discussing for past 3 lectures, and discuss Galilean notion of relativity, which will be the precursor for the special relativity. We will discuss in due course of time. So let's start with the brief recap. So the main content of the Newton's law of gravitation is encoded into this formula, that is, given this gravitational field, if we specify this curl and divergence, which is given by these two equations, that is curl of g is 0 and del dot g is minus 4 pi g Newton times the density, which is the density of the gravitational mass, or we will simply call it as mass of the object that is producing the field at the point x. And just like in electrostatic, we know that if you specify curl and divergence of the vector field and give the appropriate boundary condition, then we can solve this G or the vector field in this case uniquely, and that's it. Now, the first equation implies that this can be written as the gradient of a scalar function, and that is we call a scalar potential, and which satisfy the Poisson equation, which is this. So it simplifies our computation, because instead of solving this vectorial quantity, basically you have to solve the 3 components of the gravitational field. But if you are working with this scalar function, you can simply deal with one single function and solve this Poisson equation with the appropriate boundary condition, and then you can get back the solution for G. Now, we have also discussed various important properties like uniqueness, existence of the solution of the Poisson equation, as well as mean value theorem, Earnshaw theorem in the previous lecture. Please keep that in mind. Another thing that we discussed is the tidal force. We consider a point P in a reference frame whose origin is in free fall. Then with respect to that origin, if the position vector of the point P is x, then we can write down the expression for the tidal force, which is shown here. And please check that if you take the divergence of this in the vacuum, that is when there is no matter density present, is rho equal to 0, it vanishes. In fact, this del dot f equal to 0, this statement is equivalent to the statement of that in vacuum the gravitational field can be solved by solving the Laplace equation. So in vacuum, the Newton's law of gravity can as well be reformulated in terms of this tidal force. And the important point you should keep in mind that this tidal force plays a role to distinguish between the effects of gravity from that of the inertial or the pseudo force. Basically, you can do a local experiment to measure the tidal force and say that, okay, this is happening due to the gravitational field, not due to some inertial force. And this f follows as 1 over r cube. It should be evident from the expression that we written down earlier, because it's actually a derivative of the gravitational field, which is given here. So this is the gravitational force. So if you take one more derivative of inverse law, it falls off as 1 over r. Okay, so now we will move on to discussing this Galilean notion of relativity, and this will serve as a precursor for the special relativity. So the main point of any relativity is that it gives us a set of special reference frames, which we call inertial reference frame, and also they give us the transformation law of various physical quantities if we move from one frame to another. That is even true for special relativity. So for this case, the inertial reference frames are those frames where the Galileo's law of inertia holds. Remember the Galileo's laws of inertia, that absolute motion does not exist. So if you do an experiment in a windowless lab, you will not be able to distinguish whether it is at rest or moving with a uniform velocity v. So these inertial reference frames are the frames where these holds. So any frame that moves with a uniform velocity with respect to other frames, they can be considered as inertial reference. So Galilean Relativity gives this notion of so-called this global inertial reference frame, where all space is homogeneous and isotropic, and all time, which runs from infinite past to infinite future, is also homogeneous. So what do we mean by space is homogeneous and isotropic? So homogeneous means that there is no preferred location in space. So you can do your experiment at any point in space, and if you are running an identical experiment, it should give the identical result. So mathematically, this means that you can set your origin at any point in space. And what do we mean by isotropic? It says that if you orient your apparatus and run the similar experiment, it should give the similar result. And mathematically, this means, for example, let's say you choose the x-axis and you can orient your x-axis after fixing the origin at any direction, and pretty much things are equivalent. So there is no preferred direction in the entire space. And also, all time is homogeneous, which means that essentially you can take any moment of time and set your origin at them. There is no preferred location when time runs from past infinity to future infinity. You can take any point in time and start your experiment from that point. Okay. And you can consider this as an alternative definition of inertial reference frame, which is equivalent to defining it by saying that inertial reference frames are frames where Galileo's laws of inertia. Okay. So now for our purpose, we will consider two different frames. One we called S, which is also we called lab frame, which is attached to the lab, which is at rest. And let's consider an event at this point marked here. So to specify it, we need to specify the location of it, that we have to specify the 3 spatial coordinates, and also we have to measure the duration of the event, that is we need a clock to specify the time. So we specify t and the x here. Now the same event will, if we move to another reference frame, which we denoted by f prime, will go to this point p prime, and it will be characterized by this coordinate, which is t prime and x prime, x vector prime, which again is x1 prime, x2 prime, x3. Now, what is this s prime? S prime is a moving frame, or you can call it a boosted frame, which moves with a constant velocity with respect to the s. Okay, so you can think that this lab frame is attached to the laboratory, and you are doing an experiment, let's say with fluids, and the molecules are moving with a uniform velocity v, and the frame, this s prime, is attached to that molecule itself. So from the molecule point of view, this is a rest frame, and with respect to the lab frame, it is moving with a constant velocity v, which we call boosted. So we will use the same terminology when we will go into special relativity and set the Lorentz transformations. So please keep this in mind. So now in the context of Newtonian relativity, space-time are absolute, which means that if you measure an interval in space, it will remain the same in every inertial frame. And if you measure an interval in time, delta t, which will also remain same in every inertial frame. we are going to use this fact. For the moment, we are going to use the fact that time are absolute to derive the most general transformation law, which relate this tx, these coordinates in s with the coordinates s prime. So let's do that. So as we are working in the context of Newtonian relativity and with the inertial reference frame, we expect that the Newton's law holds for both an s and s prime, and it takes the same form. So at f prime, we wrote down this Newton's law. This is the vector form, and in the component form, this takes this form. So I denote the three components if you are working in three space dimension, which is 1, 2, 3. You can think of like the x, y, z component. Okay. And also similarly, the same form of the equation holds at s prime. So we denote these by superscript prime. So f prime is equal to m prime and d2 x prime dt prime square, and in the component form this is given. So prime denotes that it is in the boosted frame. So we know that mass of an object is a frame invariant constant. So we will set m equal to m prime. So now we use the fact that the time is absolute, which means that the time interval dt prime is equal to dt. And if you do that, then f prime becomes this. So we have replaced the dt prime by dt in this formula. Also, it is evident that the magnitude of a force is frame invariant. In fact, please think about why the magnitude is frame invariant. And how do you define the magnitude, which is here, basically. So repeated indices summed over, it is basically dot product with itself. And you can think about this is like a magnitude square. Okay. We are not bothering about the square. You can always square these two quantities. So this statement is basically reflecting that magnitude is invariant, frame invariant. And then write that f prime I is some Oij times fj. What is this Oij? Oij is the ijth element of a matrix O. Remember, this is like a vector quantity. You can represent it by column. Then this is basically you are multiplying a matrix with a column vector. And component form, this is what it looks like. So now if you put this into this equation, then we simply get this. And after readjusting, it implies that this condition should hold on the O. Remember, the O is giving you the transformation matrix for the S when you are going from one frame to another. Now, if you look at it and if you bring it into the matrix multiplication notation, which is nothing but O transpose times O is the identity. So delta ijk, remember, is a Kronecker delta. That means it is 1 only when j equal to k and 0 otherwise. And you can write the transpose, the element of the transpose matrix in this following way I shown. So O transpose, the element of is j of I, which is basically the element ij element of the O. So it implies that this O is an orthogonal matrix. Now also note that the component of this O is independent of space and time. So finally we can write at in the S prime when F prime is like O times F. And we equated it to this expression of F prime. Now we can put back the expression of F, which is simply d2x by dt square. And we can rearrange this equation to get this. And you can see that importance of being this being the components of O being independent of x, because otherwise we would not have got this equation. So we can easily solve this and we get this. So in this case, v and ai are two integrating constant. Remember, the v and ai, these are vector quantity, so they are subscript as the three of. Basically, you are solving three equations, right? And finally, we arrive at the most general transformation rule, which relates the x prime t prime with x and t. which is summarized in this box. So first one we just derived, and second one follows from the fact that absolute time is absolute. That means that if you take the time interval, it remains same in the both the frame. So b is some constant, so of course it means that dt prime is equal to dt. So in the three vector form, which might be more familiar with you can rewrite this equation in the following way. Remember, x is like a vector, you can represent by column, and this is like in the matrix multiplication notation, the matrix is multiplying a column vector. And again, v and a are the some constant vectors, and b is some constant number, and these are known as Galilean transformation, which enables you to transform physical quantity from one inertial reference frame to another inertial reference frame within the context of Galilean Newtonian relativity. So now what this O rotates this frame S prime with respect to x, that should be evident. And V is we call the Galilean boost, or the uniform velocity with which this S prime is moving with respect to x. And what is this A? A is basically the location of the origin in S in the new coordinate system in the frame S prime. And what is this B? B measures how the clock in the prime coordinate is leading the clock in the unprimed. You can actually easily see this just by putting this x and t to 0 and convince yourself that what I just said is right. Now, we have found the most general transformation rule, and let's try to prove that the absolute length in Galilean relativity on other words that the length interval remains invariant under this transformation. Okay. So in the let's start in the S frame, and we define the length, which is given here, square root of this delta x mod square. Delta x is basically the difference between the coordinates, and of course delta t has to be set to 0, because for example, suppose you measuring a rod, you have to measure two endpoints faithfully to have a make sense of this length. This is be familiar with. Now the S prime, delta x prime transforms accordingly. So this is just a small differential version of the previous transformation that we have wrote down. And of course delta t is 0, so delta x prime is just O times delta x. O, remember, is the orthogonal matrix which satisfies this condition. And then it is evident that you compute L prime, which is mod x prime square whole square, and then you plug this and you get a factor which is O transpose times O. Just do it carefully, keeping in mind these are matrix multiplication. You will see that O transpose times O will come and set it to identity because O is orthogonal, and you will see that this is equal to the L, and that is pretty much makes sense, because you know that in this context, if you rotate, the length of the vectors remains invariant. So we will stop here, and thank you for listening.